Okay. So, as I was saying, the uh, a hydrogen ion is just is just a single proton. All right. Now, in water, so we're used to talking about hydrogen, um, like as being kind of like an H plus when an acid gives off a hydrogen in water. But in reality, what happens is this. So it's a little more complicated than what we normally have talked about. In water, um, the hydrogen ion will actually sort of bond with a water molecule and form what's called a hydronium ion. That's this deal, the H3O plus 1. Okay. So in water, the hydrogen ion typically will join up with a water molecule and form what's called the hydronium ion. In general, for acids and bases at a simplified level, we consider the hydronium ion and the hydrogen ion essentially the same thing. Because the way you get to this is just when it's dissolved in water, a water molecule plus the hydrogen. Okay? We good on that? All right. Larger clusters are also possible, blah, blah, blah. We're not really going to deal with those. And then here it says exactly what I just said. We use H plus aqueous and H3O plus interchangeably. So essentially the same thing. Okay. All right. Proton transfer reactions. Um, According to this Arrhenius definition, an acid increases hydrogen and a base increases hydroxide. Bronsted-Lowry, however, looks at this from a more um, generalized viewpoint of it's just what is going to happen with the protons. Are they going to give up a proton or a hydrogen, or is it going to accept a hydrogen or a proton? Okay, so an acid is anything that donates a hydrogen or gives up a hydrogen or a proton. A base is anything that accepts a hydrogen or a proton. Now, by the way, when they say species is essentially any kind of, like it's just basically any kind of substance. Therefore, a Bronsted-Lowry base does not need to contain hydroxide. So we actually talked about this earlier this year when we were talking about strong versus weak acids and bases. And I just kind of told you guys to memorize it, that NH3 was a weak base. Okay. Um, so NH3 is a base. In Bronsted-Lowry, it's actually a little easier to understand why. So what happens in Bronsted-Lowry is you have ammonia, NH3, in water. And what happens is a hydrogen, water breaks up. When you put the ammonia in water, water breaks up and it gives a hydrogen to the NH3. So the NH3 takes a hydrogen, the water loses one. So you end up with NH4 plus 1, ammonium ion, and look what's left over, hydroxide. So even though the NH3 doesn't have a hydroxide to like give up, it creates a hydroxide when it accepts the hydrogen from the water, because what's left over is the hydroxide. Does that make sense? Sort of, somewhat, not at all. Okay. Um, so these equations, you see acid-base equations typically written with the equilibrium arrows, like the double arrow either way, or sometimes it's like this, but the arrow looks like a kind of like two half arrows. Those are essentially the equilibrium arrows, meaning the reaction can like go both ways. It reaches like an equilibrium. Okay. All right. So we have, and we're going to talk about them a little bit on the next page. We have what are called conjugate acid-base pairs. Okay, and I'm gonna actually talk about those and then come back to this and talk about and sort of identify what these are. So, an amphiprotic substance can behave either as an acid or a base. Water is an example of an amphiprotic substance. And I'll explain that in a second here. Okay, so let's go to conjugate acid-base pairs here. Whatever is left of the acid after the proton is donated is called its conjugate base. Similarly, a conjugate acid is formed by adding a proton to the base. So basically, what you get is let me see. I guess I can write this on the side here. An acid will turn into its conjugate base, and a base will turn into a conjugate acid. Okay. And these are called conjugate acid-base pairs. Now, they give you the whole, like, they're throwing, just if you guys look at this, so just so you understand what it's saying, they're putting like the X in as like a generic variable for the anion or whatever. Let me just show you on this page with what they gave us here. I think it's a little easier. Okay, so for example, if we look at this equation, what happens to the NH3 from the left side to the right side? Gains a hydrogen, right? So if it gains a hydrogen, that means if it accepts, so if it's accepting a hydrogen, that makes it a base, right? Anything that's accepting a hydrogen is a base. So that means the base is the NH3. That's what I have here. Everybody okay with that? From the left side to the right side, it gained a hydrogen. Now, that makes the NH3 the base. It makes what it turns into the conjugate acid. So the thing that it turns into is the conjugate acid, the NH4 plus. Okay. So here, water, what happens to water from the left side to the right side? Loses a hydrogen, right? It donates it, it gives it up. So if it donates a hydrogen, that makes it an acid, which means what it turns into is the conjugate base. So this is the acid because it's giving up a hydrogen. The thing that it ends up as is the conjugate base. So one side is going to be one, the other side is going to be the conjugate opposite. So if you start with a base, it turns into a conjugate acid. If you start with an acid, it turns into the conjugate base. Everybody okay with that idea? Okay, now, down here, I'm showing you this because they didn't really talk too much about this, but so look at HCl here. Oops, sorry, move it over a little bit. What does HCl turn into? The Cl minus, right? So what happened to it? Did it gain or lose or give up a hydrogen? Gave up hydrogen, right? So if it gave up a hydrogen, that makes it, donates, makes it an acid, right? So if this is the acid, what is this? Good, conjugate base. Okay, which means, oh, and here's the other nice thing about this. If it's an acid-base thing, acid-base reaction, if you have an acid, you have to have a base. Because for something to give up, that means something else has to accept it. So you know, like if you identify an acid in there and you're having a hard time, like you know that there's a base in there somewhere, you just got to kind of find where it goes. So that means that the water, if we look, the water accepts a hydrogen, right? Turns into hydronium. So that makes water the base, which makes the hydronium the conjugate acid. Everybody okay with that? Now, this helps to explain this highlighted part here. Look at water here. Water's a base because it accepted a hydrogen, right? Look at water here in this one. Water's an acid. A substance that can be either an acid or a base is called amphiprotic. So that's the amphiprotic. Okay, from here and there you can see it. It can do both. How are we feeling? Is that making sense? Okay. I'll let everybody get that down and then. We good? Okay. Okay. So this part right here is just talking about exactly what I just went through, showing you how to figure out what's the acid, what's the base. Okay. So let's before we go on too much, let's go to the practice problems real quick. Let's do the first one here. All this is identifying conjugate acids and bases. Okay. So really what you need to remember, or what we need to remember as we're doing these, is conjugate acids are going to be things that, I'm sorry, not conjugate. Acids are going to be things that donates hydrogen, gives up. Bases are going to be things that accept. So here, they're saying that these are acids. If they're acids, that means they have to give up a hydrogen, right? So this actually is not hard at all. All you're going to do is, so we're going to start with like HClO. You start with what they give you, HClO4. And the conjugate base is going to be the exact same thing minus a hydrogen, and you've got to change the sign based on the fact that we lost an electron. So it's going to get a +1. So like this becomes ClO4, or I'm sorry, not a +1. It's going to become a, because you're losing a positive. So it's going to become a negative. So this would be a negative. ClO4 -1. Okay, so H2S is going to become HS -1. pH4 +1 is going to become pH3 with no charge, right? Because it went from a +1 to a neutral. And HCO3 -1 is going to become CO3 2 negative. So these would be the acids, these would be the conjugate bases. How do we feel? Like, makes sense so far? You're just basically getting rid of a hydrogen and changing it by a negative, like a -1 as we go there. All right, what about the conjugate acids for the bases? What are we going to do for these? Yeah, just the flip of it, right? The reverse. So for example, the first one, CN -1. So if it's a base, it's going to gain a hydrogen. So we're going to do HCN, and then we're going to add a +1 to the charge, which this was already a -1, so it becomes just HCN. Right, that would be the conjugate acid. SO4 2 negative. What's that going to become? Perfect. Good. You guys got it. H2O becomes H3O +1, the hydronium ion. Good. And the HCO3 -1 becomes H2CO3. All right. You feel okay on those? Like, that makes sense? Okay. So let's go to the relative strengths of acids and bases part. And by the way, the page 672. The page 672 is actually the sheet that I handed you guys out. The extras. It's this thing. So I typed it up, and I actually added some other ones to make it a little more complete. But so this is the thing from page 672. So similarly, it's kind of opposite. The stronger an acid is, the weaker its conjugate base will be, and vice versa. Okay, we can categorize we can categorize acids and bases according to their behavior in water. And we've already done this to some extent. Way back when we were talking about strong acids, weak acids. Strong acids completely transfer protons in water or completely dissociate. Weak acids only partially dissociate in aqueous. So remember, it's some of it like dissociates or breaks apart, and some of it stays together as a molecule. Substances with negligible acidity do not transfer protons. So those would be things that really aren't acidic or basic. They don't transfer protons at all. Those would be considered like non-electrolytes. So remember, like, we had strong electrolytes, weak electrolytes, and non-electrolytes. Acids and bases are a category of electrolyte but they still qualify as electrolytes because they're either giving up or accepting, like dissociating in water, like that, and the hydrogen movement. All right. Okay. In every acid-base reaction, the position of the equilibrium favors the transfer of a proton from the stronger acid to the stronger base. So H plus is the strongest acid that can exist in equilibrium. OH negative is the strongest base that can exist in equilibrium. So we use those that's why they use those to define acids and bases with the Arrhenius definition or whatever, because those indicate the presence of acid or base, because as they turn into one or the other. So if you look at the example I have written here, this is hydrochloric acid and water. Now you guys know in general that like hydrochloric acid is a pretty strong acid, right? So we get the acid, the HCl, and here water is going to act as a base. It says stronger if you're having trouble. I know it's in pencil, sorry. Okay. Okay. The hydrochloric turns into Cl negative. That's the conjugate base, goes with the acid. And the water turns into H3O plus, or the conjugate acid. So the equilibrium shifts to the right. And I'm trying to think of a good way to do the equilibrium shift to help you guys with it. Basically just comes down to the equilibrium shifts opposite. So here, we'll worry about that in a second. Let's do the second, oops. Let's do the second page of the practice, the equations for proton transfer reactions. Let's do this first, and then we'll worry about the shifts. Okay. So this is sample exercise 16.2 from 671. The hydrogen sulfide ion HSO3 negative 1 is amphiprotic. That means it can act as either what? Acid or a base, right? Acid or a base, okay? Write an equation for the reaction of HSO3 with water in which the ion acts as an acid. Then identify the conjugate base pair. So let's start off with our ion. So we've got HSO3 negative 1 aqueous plus H2O, the liquid, right? Okay. Now, okay, we want this ion to act as an acid, so it has to do what? To be an acid. It's got to flip the other way around, flip it. Yep, it's got to get rid of it. So this wants to get rid of it, right? So it's going to be SO3 negative 2. Okay, which means what does the water become? There you go, H3O plus, like that. Okay, then identify, so HSO3 negative is what? Acid, which makes, what's the conjugate base then? There you go, good. And then H2O would be what? The base. And then obviously the only thing that's left is the H3O plus 1 as the, there we go, good. Okay. Now, I'm going to pause this for a second. Okay, so should be something kind of like this. Oops. Yeah. H2SO3 plus This is going to be OH negative 1. That. So far, so good. Great. Then if we did it right, the HSO3 in this case should be a what? There you go, base, which means it turned into the H2SO3, which is the good conjugate acid. And that leaves us with the water acting as the acid, and then what the water turned into, the OH negative, is the conjugate base. Okay, how do we feel so far? Like stuff making sense? All right. Check something here. Okay, you know what? So there's nothing. I'm just going to stop here.